అవునా? ఆమె ఆమె ఈరోజు వచ్చిందిగా. ఆహా! మళ్ళీ ఈరోజు అటెండెన్స్ కూడా కన్సిడర్ అవుతుందా?
హలో. హలో. హాయ్. హలో. 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 ఈకోగా ఈకోగా హలో. హలో. दो फैसल भाई
Good afternoon, everyone. Good afternoon, everyone. On behalf of the Spurti Engineering College, Hyderabad, I warmly welcome you all to the 5-day online national level faculty development program on intelligent computing frontiers, emerging AI paradigms to quantum computing, organized by the Department of CSE AML. We are delighted to have with us faculty members, research scholars, and professionals from across the states joining us to explore cutting edge technologies that are shaping the future of education, research, and industry. About our institute, Spurti Engineering College, established in 2004, has been excelling in research, innovation, and entrepreneurship. With NAC A grade accreditation, AICTE approval, and affiliation to JNTUH Hyderabad, the college has consistently ranked among the top engineering colleges in Telangana, including the 11th rank in Telangana Engineering Colleges and 8th rank in research capabilities as per the Times of India Ranking Survey 2025. About AML department, the Department of Artificial Intelligence and Machine Learning at Spurti Engineering College was established in 2020 with an initial intake of 180 students. Owing to its rapid growth, strong academic foundation, and increasing demand for AI and ML professionals, the department has now expanded to an intake of 300 students. The AML department is committed to nurturing future ready engineers by focusing on cutting edge technologies, research, and industry collaborations with a dedicated faculty team, modern infrastructure, and student centric initiatives. The department continues to prepare graduates who are well equipped to meet the challenges of the AI driven era. We are deeply honored to have the guidance of our chief patron, Sri S. Jagan Mohan Reddy, Sir, Secretary and Correspondent of Spurti Engineering College. Sir, your vision and constant encouragement have always inspired us to strive for excellence in academics, research, and innovation. We extend our heartfelt welcome to you, sir. We are equally privileged to have the support of our patron, Dr. K. Srinivas Rao, sir, Principal of Spurti Engineering College. Under your leadership, the institution has consistently scaled new heights in quality education and research. We extend a warm welcome to you, sir. To give us an overview of the FDP, I now invite Mr. Mohammad Afzal, in charge HOD, Department of AML, to give a brief on FDP.
Thank you, madam. Good afternoon, everyone. This is Mohammad Afzal, Assistant Professor in CSC AML Department, Spurti Engineering College. We designed this FDP to empower educations with knowledge and hands-on exposure. Throughout the FDP, we cover large language models on day one, generative AI on day two, agentic AI on day three, retrieval augmented generation RAGs on day four, quantum computing on day five. We got some eminent resource persons from different prominent institutions all over India. On day one, to cover the topic, large language models, we have Professor Anish Srivallabh, Assistant Professor, Department of CSC, Bitsbilani, Hyderabad. To cover the day two topic, generative AI, we have Dr. Balaji Banotu, NIT Tiruchirappalli, Tamil Nadu. To cover the day three, we have Dr. Dinesh Nayak, Assistant Professor, NIT Karnataka, Surathkal. To cover the day four, we have Dr. Pabitra Mohan Khilar, Professor CSC, NIT Roorkela. To cover day five, we have Professor Manish Kumar, Associate Professor, Department of Mathematics, Bitsbilani, Hyderabad campus. The FDP aims to bridge the gap between academia and industry, foster interdisciplinary collaboration, and prepare educators to guide students towards future technological challenges and opportunities. We extend our heartfelt gratitude to the resource persons for sharing their experience with us. Thank you. Over to you, Veena ma'am.
Thank you, sir. Now, it is my honor to invite our chief patron, Sri S. Jaganmohan Reddy, Secretary and Correspondent of Spurti Engineering College, to kindly address the gathering.
Good afternoon, everybody. I welcome all for this 5-day FDP program inauguration conducted by AML Department of Spurti Engineering College. A good initiative taken by the department to conduct this 5-day FDP with the relevant topics of as per today's requirement. We all know, we all of the faculty member who are participating might have done their BTechs or MTechs, PhD long back. That time, these LLMs or agentic AI or generative AI, these are not quantum computing. These are not the part of your curriculum, but you are the people who are teaching the student today. And definitely, these knowledge is very much important. And keeping with this requirement, this gap, and I really appreciate the AML department for choosing this topic and both this AI and quantum computing. And definitely the resource persons selected also very eminent people in this field. Definitely their knowledge and experience definitely going to enhance your knowledge. Definitely it is going to equip you for coming academic year to give your best as a faculty. And all the participant who registered, and appreciate your enthusiasm for taking part this 5-day. And definitely this time whatever you are sparing for this, definitely it is going to help you with the right resource person chosen by the department. And wish you all the best. And once again, I appreciate the department for taking this initiative. Thank you very much.
Thank you, sir. Thank you, sir. for your constant encouragement and visionary leadership have been the guiding force behind this FTP. With your blessings and guidance, we are confident that this FTP will be a great success. With this, let us begin today's session through the objectives of the FTP. The objectives of the FTP focuses on cutting-edge technologies, transforming education, research, and industry, equips faculty with knowledge of large language models, generative AI, agentic AI, retrieval augmented generation, and quantum computing. It also helps educators integrate advanced technologies into teaching, research, and curriculum design. It provides expert-led sessions with exposure to real-world tools, methodologies, and applications. It enhances academic and research capabilities of participants. FTP promotes innovation and interdisciplinary collaboration among faculty. It bridges the gap between academia and industry through practical insights. It also empowers educators to prepare students for future technological challenges and opportunities. It also contributes to the institution's excellence in teaching, research, and innovation. Let's see the outcomes of the FTP. At the end of the FTP, participants will be able to gain conceptual clarity on LLMs, generative AI, agentic AI, RAGs, and quantum computing. They also will be able to acquire practical exposure through hands-on sessions with open source tools. They will be able to understand ethical, compliance, and industry perspectives of emerging AI technologies. With this, they be prepared to integrate advanced AI paradigms into academic curricula and research initiatives. With this, let us begin today's technical session, and look forward to insightful learning. Once again, we welcome you all to the FTP on Intelligent Computing Frontiers, Emerging AI Paradigms to Quantum Computing. Let's embark on this exciting journey together. Dear participants, as we are waiting for our resource person to join, as he has some technical glitch, so we'll wait for 5 minutes for the resource person to join. Thank you.
Good afternoon, participants. Our resource person is already in the room. Anish sir. Am I audible to you, Anish sir? Sir, you are already presenter, sir. You can unmute yourself. Hello, sir. Anish sir.
Good afternoon. Am I audible?
Yes, sir. You're audible, sir. Anish sir. You can continue,
Is
sir.
Is the screen visible?
Yes, sir. Screen is also visible.
Okay.
You
So
can
I will
continue
just
the session.
switch between slides. I wanted to show all of you the architecture of a transformer. So this is the basis of modern LLMs. So as you can see,
Hello, sir.
there are 5.
Hello, Anish
Come
sir.
again? Yeah.
Anish sir, this is Veena, one organizer.
Yeah.
Sir, we would like to invite you with your short introduction, sir. Allow us
Okay,
to do
fine.
that.
Yeah. Okay. Go ahead.
Yeah. Thank you, sir. It's my privilege to introduce our distinguished resource person for day one of this faculty development program, Professor Anish Srivallabh Chivukula, Assistant Professor in the Department of Computer Science and Information Systems, BITS Pilani, Hyderabad campus. Professor Anish brings with him a rich blend of academic, research, and industry experience spanning over 16 years. He has worked extensively in R&D for 4.5 years, academia, and industry for 7.2 years, making him a well-rounded expert bridging theory and practice. Sir, research focuses on machine learning, deep learning, adversarial learning, data mining, and computational algorithms. His work has been widely published in reputed journals of conferences with impactful contributions such as adversarial deep learning models with multiple adversaries, IEEE, transactions on knowledge and data engineering, game theoretical adversarial deep learnings, IEEE, transactions on knowledge and data engineering journals, big data analytics, system algorithms applications in Springer. Recent innovations in deep learning based encryptions for medical image and cybersecurity applications using reinforcement learning, BITS Pilani, Google Scholar. He is also a co-author of the book Adversarial Machine Learning: Attack Surfaces, Defense Mechanisms, Learning Theories in AI, published by Springer Nature, which is a key reference in this field. Professor Anish is a passionate about mentoring students and researchers, encouraging long-term projects that explore cutting-edge AI paradigms. His expertise in adversarial learning, quantum-inspired computing, and applied AI systems makes him an ideal speaker for today's session. On behalf of Spurti Engineering College, we extend a warm welcome to you, sir. We are eager to learn from your insights on emerging AI paradigms and intelligent computing frontiers. Sir, we now invite you to kindly take over the session and enlighten us with your expertise. Thank you, sir. Over to you, sir.
Okay. Yeah. So good afternoon, everyone. So as a motivation slide, I have put this where we want to understand the architecture of the neural network and see how it is different from the other networks which are there in the literature, which you have been using till now, like multilayer perceptron. And here, as you can see, there are different blocks. So if we count all the blocks, we get 5 blocks. And this 5-block unit is the building block for a transformer. That 5-block unit is called a transformer. So we have to understand how data is being processed in terms of getting represented in a manner that is suitable for giving as input to these blocks. Then there are mechanisms like attention mechanism, which are introduced as neural network layers. Then there is an algorithm like feed-forward algorithm, which is going to train the weights of the neural network. Now, somehow this block, when it is put in a nested fashion, that is block within block in series and parallel, we will get the result which we want. That is, we prompt a LLM and it gives us a response for a query. So is this response valid or not? And then is it relevant to our query or not? Do we require more data? And how much hardware do we require to train this model? So these are the kind of questions which we have to answer in terms of the design of the system. And in general, nowadays there are very big LLM models available. So I will, when the slide comes, I will highlight that. But you find language models like this, where it starts with statistical models and it ends with transformer models. There is an evolution of the models going from several decades ago to last 5 years, where neural networks have been increasingly used in this area, whereas originally it was a mathematical statistical kind of area. And then we call these models as large models because the total number of parameters in these models is large. Order of millions and billions of parameters, which are the weights in the neural network, must be estimated for the given data set. So for example, if you take Hindi data, you need a corpus of Hindi. And then suppose you are searching for something Hindi poetry. You want to check some Harivansh Rai Bachchan's poetry against something which was written 500 years ago. So this corpus must be available to the language model. And then the parameters will encode this information in a manner that we can consume it. So there are many architectures available in the literature. I will go through some of those architectures. It's a kind of a question answering system, and it is for particular domain like healthcare domain. So we have to build language models which are going to process particular languages. So right now, European and English language is the widely used language, but other languages, for example, Chinese language or Hindi, can also be used. Then the modeling is basically to do with the neural models. That is, we have to understand how to train the neural network to approximate the function which we want. So there is like an input output, like there is a X and there is a Y, which is an output coming from X. And neural network is like a function f, y equal to f of x, where f is relating x with y, approximately. Y is approximately equal to f of x. So now this f can be, in general, any function. Like it can be sin x, it can be x squared, it can be sin x by x, so on, any function. And in general, we don't know the equation for the function also. That is, we don't have a closed form solution. We only have data. For example, handwritten digits data. And we should be able to extract information out of it to get the output which we want. Like which digit is it corresponding to? Suppose there is a 7 which is written. Output should be this is the image for a label 7. And similarly, if there is a 9, output should be 9. So similarly 0 to 9. And then this has to be obtained from the pixel information which is there in the, let's say, black and white image for the digit 7. And there will be multiple channels from which we will get this pixel information. Each pixel will be like a number going from 0 to 256. And that tells us how bright that pixel is. And different combinations of pixels will give us the geometry of the image. And this information has to be extracted out to get this function f. And unless we have the model, we don't know the function. So it is a data-driven solution. When we give a 7, it gives output, this is a 7. When we give a 9, it gives output, this is a 9. So how do we learn these functions? That is the goal of the training algorithms of the neural networks. And the language aspect is to do with the architecture of these neural networks, where you have sequential models, discriminative models, etc. Where how do we put together the neural network layers to encode the information from the raw text and get the answer to the query which is relevant. That encoding mechanism is given in the neural network layers. So these are the building blocks. Now let us see an introduction to deep learning. And as the slides come, I will discuss certain points of interest. Once we are familiar with deep learning, I will introduce quantum deep learning. So when you look into the literature in this area on how to use machine learning and deep learning. So essentially, AI is the area, artificial intelligence. Inside that, machine learning is a subset area. And inside that, deep learning is another subset area. Now inside that, quantum deep learning will be one more subset area. So we want to understand a very vast area like AI. And in that, we want to focus on our interest and our specialized model or solution for the given problem specification. So how do we go about doing that? If we just do a Google search, for example, we will find many keywords to search for and many results. And it will be a kind of information overload, like how it's shown in this slide. You will find different types of models, different ways to process data, different theoretical frameworks, different connections which machine learning has with other areas of mathematics and other subjects like electrical engineering. And then you want to see which one is relevant for the problem at hand. So one way to deal with this is to create mind maps where you organize the information into different categories. For example, theory category, paradigm category, technique category. In theory, we will get terms like bias variance trade-off, complex computational complexity, so on. In paradigms, we will get like supervised, unsupervised, reinforcement, etc. learning. In models, we will get linear, non-linear. In non-linear, we will get graphical models, support vector machines, singular value decomposition, so on and so on. When we build these models, we have to train the neural network parameters, and for that we use different techniques like regularization, validation, pre-processing, so on. So this is one step to organize the information. Then we may use any existing library. So use any Python library, and you'll find in machine learning area, which is part of artificial intelligence area, for supervised learning. In classification, you'll find a perceptron model. So how to use a perceptron, how to train it, how to apply it on a particular data set, and then also use this model in a particular workflow for a particular problem statement will be facilitated by such a library in Python. But we should know this taxonomy, where how to go from machine learning to supervised learning to classification or regression to perceptron. And to do this, we have to study the area of supervised learning. So then we connect with the previous slide and then say, okay, we are talking about supervised machine learning under the framework of bias variance trade-off, and we are looking into regularization using a neural network. So we have to have this information about these building blocks to define what is the problem solution. Similarly, suppose we have built a regression or a classification model, and we want to improve it in terms of some kind of a performance criteria like accuracy. Then there will be variation of the problem formulation, like semi-supervised learning, unsupervised learning. So we start with supervised, then we get into semi-supervised. So what is the difference between these two? The models are similar. There is a classification here in both supervised and semi-supervised. But if there are no class labels available, that is, we don't know the handwritten digit corresponds to 7 or 9. It could be any geometry, any combination of pixels. Then we use semi-supervised learning, and we have to shift from classification to clustering. So we have to define the task at hand. The original problem was to do, let's say, handwritten digit recognition. So recognition was the problem. Now, when we do it in our thinking, we have a process to do it, and we will do the recognition in one way. Is the algorithm doing the same thing? This is the gap which we have to bridge. Once we have a problem statement which we have formulated, let's say mathematically, we have to map it to one of the algorithms which will solve for that problem. Now that if that algorithm was earlier classification, that would work only if we have the class labels. That is we know a 7 is a 7, a 9 is a 9. Given an image of a 7, we can output label 7. Given image of 9, we can output label 9. Suppose we know this information of 7 and 9, then we can use classification. If we don't know and we only have pixels, we should use clustering. So first we have to formulate the solution in terms of the algorithm, which is mapping with the thought process or the mathematical model, which is giving us the problem statement or formulation. So once we have a solution, we try to optimize the solution. We keep on trying to improve. For example, how we do in data structures and algorithms, we try to improve the efficiency of the algorithms there. Like that, here we want to improve the performance of the algorithm in some way, not only efficiency, but also accuracy, robustness, convergence criteria, optimization criteria, so on. And this has to be deployed into an underlying system, a real world system like a mobile phone. So we have to integrate the algorithm with the system. And system has some constraints. For example, mobile has 8 GB RAM. In 8 GB RAM, the clustering algorithm must be executing for the given data. So how much data can it process? How many handwritten digits can it process? 1,000, 5,000, 1 million, how many? That depends on what is the capacity of the hardware. So within the constraints of the mobile phone, we should be able to run the clustering algorithm and get the result of the cluster. This is one kind of a performance criteria for this algorithm. So like this, we define several problem formulations for machine learning. It could typical ones are supervised, unsupervised, and reinforcement, where supervised means we have class labels like a 7 is a 7, or a cat is a cat, a dog is a dog, a 9 is a 9. Like that, we have class labels, or we do not have class labels and we are just doing exploration of data. In between these two scenarios is the semi-supervised scenario. And then reinforcement is a different way to design. It is a kind of a feedback loop procedure. So there is a concept of a AI agent. So nowadays there is agentic AI, where agent is a kind of a program which is taking input from the surrounding environment, like from a sensor. And it is making some reasoning on the program, and it is giving a response to that input which is coming from the sensor. And that sensor is realized in the physical world like a robot with like an actuator. So there is a feedback loop which is created on top of the program, and the program is doing something which we want. Like it is giving us the result of the query. We have given the prompt, it has to give the result. So instead of searching on Google search, where it will give you URL based result. So if we are giving a keyword matching like with Sachin Tendulkar, if we say, then matching with that, all the results like related to cricket, related to Bombay, then related to one day match, test match, like this, different URLs, web pages will be retrieved by the Google search engine. Whereas the LLM is having several such agents, and it is doing kind of reasoning. It is saying, okay, when they are talking about Sachin Tendulkar, is the question with in the context of a one day match or a test match? Is it in the context of retrieving some statistics or the awards which Sachin has? So on, so on, right? And then this context will be inferred from the keywords or the query which we are posing, the prompt which we are giving to the LLM. And the feedback loop is there, which is doing some reasoning behind the scenes using some patterns, and it is giving a result which we want. That is, for example, one day batting averages of Sachin Tendulkar from 1985 to 1995. So this information is being retrieved from the internet. There is a web page like ESPN web page is there, and it has all these numbers. Now the summary of this has to be calculated, for which an average calculation has to be done. Now this average calculation, the LLM will figure out on its own. We only have to say calculate the average batting average in one day matches. And then it will calculate the average based on the formula which is used in statistics. And it gets the information from ESPN webpage. Not only ESPN, but so many other web pages are there. Instead of we searching through each web page, some 10, 20 web pages aggregated result it is giving us. That is the relevance. So it is easing the process of doing the search on the internet. Not only that, we can then have a follow-up question. So we can say, okay, compare this with Kapil Dev. When India won World Cup during Kapil Dev's time, what was the situation? And then when India won World Cup during Sachin's time, what is the situation? For example, West Indies was the opposing team. Then Australia or South Africa was the main opposing team. Then in the opposing team, the fast bowlers were there. So this was a problem for players like somebody like Gavaskar, but somebody like Srinath was able to deal with it. So this kind of next level investigation kind of information, which we can get from the query, can be posed as a follow-up question to the information which was retrieved by the LLM. Now, how will we do that on Google search? We will again search through several URLs, and this connection which is made between, let's say, one time period and another time period is made in our thought process. It is not made in the computation. Normally, that is the case with search engines and the previous generation of internet. But with agents, this whole thought process is automated. So the final information which we are looking for example, so how hard was it to win the World Cup for Kapil Dev's team compared to Tendulkar's team? So this is a qualitative question. The difficulty of winning the cup, and that difficulty can be answered in terms of different factors, right? So for example, India in the 1970s was not as developed as it is now. So sports people did not have all facilities at that time. And news, etc., was not available. But in spite of that difficulty, the team won. So that difficulty is not there nowadays, but earlier it used to be there. So this information, which is a historical trend, has to be extracted by the program, the agent, automatically. Normally we are making this connection, but now it is making the connection. Now what kind of algorithm will do this? That is when you have to move away from supervised learning to reinforcement learning, agentic AI, other generative AI, other kinds of algorithms. And here there is example shown of Markov decision process, which is basically a probability estimation algorithm. And using these mathematical models, we process the data and retrieve the relevant results. And there will not be one model, like how in Linux, like our Ubuntu operating system, you have several processes. So like when you open the shell and you run a command, there are several processes like list screen is there, connect with files is there, open file, edit file. All these things when you're doing, several processes are running in the background. Like that, several agents will be running in the background. And we saw the transformer architecture. Like that, nowadays, many other architectures are also coming. For example, foundation models are coming up, where there is a diffusion model, for example. So diffusion model will be based on information theoretic ideas. It will get combined with, which is based on generative modeling ideas, probabilistic ideas. So information theory plus probability theory is giving us the agent which we want. So like this, many mathematical models can be used, and there will be like a set of agents which are doing different tasks, and in coordination, they're giving us the result. So this is the area of reinforcement learning, quantum learning, and then other kinds of advanced deep learning paradigms. These are the advantages which deep learning is bringing into machine learning. Earlier, machine learning was using a neural network, but the neural network was shallow. That is, there were only few parameters to be estimated. Now, with many parameters being estimated, the function approximation which we want is getting better and better. Earlier also, mathematically, 20, 50 years ago also, mathematically, the problem was defined that you can have this kind of a neural network architecture, this kind of a algorithm to train it, and then this kind of a function approximation it can do. In this kind of scenarios, it will be useful. All this study has been done. However, now with technological advancement, like availability of GPUs, we are able to integrate concept of deep neural network into machine learning. And the architecture of the neural network will have many parameters to be estimated. And the layers of the neural network will be stacked in different ways in series parallel. So we saw one transformer model, which has 5 building blocks, which are like 5 different layers. And then combination of those building blocks will be stacked like 10 times. So there will be like 50 layers. And then the total number of parameters will be, suppose we had 100 parameters in the original 5 layers. Now, because we are using in 10 such blocks, we will have 1000 parameters. So these 1000 parameters have to be estimated in the supervised learning framework to improve upon the previous neural network architecture or the previous solution which we had. Like decision tree was a rule-based solution. A kernel-based solution was a support vector machine. And the data-based solution was k nearest neighbors. A probability-based solution was Bayesian methods. All of these can be integrated with the deep learning to improve the task of regression classification. So once we have defined the solution, scope of the work for us, we can use deep learning as an optimization tool. And this can be done for every step, which is there in a library, for example, in Python, where in clustering, you may have different clustering algorithms like density-based clustering, hierarchical clustering, model-driven clustering, high-dimensional clustering, so on. And then in summarizing the data set, which is a different task, you may have dimensionality reduction, feature extraction, selection, construction algorithms, which are basically going to summarize the data. And then there could be like a outlier detection technique, which is a counterpart for clustering techniques. Clustering creates groups, whereas outlier finds rare groups, which are different from the normal clusters. So again, for outlier detection, there will be different algorithms like density-based outlier detection algorithms, model-based outlier detection. Now, all of those can use deep learning as a tool. And hence, your original mind map, which was giving you a clue into using some library, can be improved a lot using your own solution in terms of building the architecture of the neural network, the algorithm, which is doing the machine learning, and the application scenario in which it is being deployed. In terms of all this, library is only an enablement platform. Maybe all the components are not there in it. Some parts like clustering classification we have used to create the solution. But the solution can be improved a lot using our own model. And so we should be able to implement the solution on our own. And then we will get different like application domains, such as recommender systems, user segmentation. Recommender system example is YouTube. So when you are searching through a YouTube video, other videos which are similar to YouTube are retrieved. That similarity is a recommendation problem. And similarly, user segmentation is usually in marketing. For example, in a telecom company, how to do, say, marketing and sales of the data plan in a telecom company, depending on the demographic of the users of that company. For example, college students versus, let's say, corporate employees. What kind of discount should the company give? This information will be there in the usage patterns of the data and then calls and then internet apps, etc. by those users. And that data can be analyzed to create like segments so that targeted marketing can be done. Again, in the marketing industry, that will be given as a segmentation problem. Whereas in data analytics or in machine learning, it will be given as a clustering problem. And in clustering, all the related problems may also be used. For example, statistical analysis. If we know the mean, variance, etc., or statistics of the each attribute which is used in the clustering, we can better understand the clustering. So that is univariate analysis. If we do combination, that how one variable mean is shifting according to another variable's mean, then it is multivariate analysis. So combination of all these statistical models also or mathematical models can be used to improve upon the clustering. So first of all, the business case use case is segmentation. Then the algorithm is clustering. There is a one-to-one mapping between them. Then to understand the clustering better, we will use statistics. In the statistics, we will use univariate and multivariate statistics. And combination of all this is going to give us the best clustering. That best clustering will have a real world application in the use case. So this is the workflow. The project lifecycle has to be built around this. And this has to be done for every algorithm which we build, starting from the application. So whether it is YouTube recommendation or stock market time series forecasting of the prices of stocks or the user segmentation in marketing, we have to start from there. And then we have to create the technical problem statement. Then from that, we have to see how to improve it. Then whether we are getting the performance we want and whether we can use agentic AI, deep learning, etc. So the libraries will facilitate this to some extent, but otherwise we have to build our own algorithm and model. So that is why we should have presentations like this, where we are going through the various building blocks in building our own model. So this is only one area and one library's functionality, which is shown in this mind map. Like this, many libraries will be there, like in Python, R, and then AI languages like Julia. There are many libraries available. First, we can go through all those libraries, then go back to our mind map, and then see that how to organize our solution. what is the data pre-processing, what is the modeling detail, what is the performance criteria, what is the theoretical framework, what is the mathematical model, what is the problem formulation in machine learning, how to improve it and get the optimized solution. All these things we can think about as a project. However, many people are creating these solutions. So which one to use? What I have shown you is the open source software. That is what is available for academic use. So you can have your own company and you can start using those libraries. However, do we have the skill set to build such software? So we are using Ubuntu. Can we create Ubuntu? That is the question. Are we only end users of Ubuntu or are we developers of Ubuntu? If we have the skills to develop Ubuntu, then we can create a new market and new economic opportunity around our product solution service business model. And this is where open source software will be academic use. How we do a degree before joining a job. When we join a job, many other practical issues will come. But we have to have background knowledge in the degree. So we can use open source software to create a prototype and proof of our concept. But after that, when we go take it to the market and then like a startup, we are showing like a product, there are many practical issues which will come. And there, question is, will we depend on somebody else's product? For example, will India as an economy depend on US economy? Or will we create our own product? This is the skill differentiator. And here there is an example shown of a Gartner hype cycle for artificial intelligence. It is a bit dated, but the basic concept of hype cycle is this, that you take any technology, it goes through some hype phase, then it goes through a fall phase, then it becomes a straight line parallel to x-axis, which is like the actual maturity of the technology we are looking for. So nowadays quantum computing is in the R&D stage, whereas agentic AI is in the hype stage, whereas generative AI has already, many generative AI companies have already failed. And after that, we are trying to see technology maturity and how to integrate our best practices and the lessons learned into utilizing this technology in the economy, industry, scientific advancement, etc. Okay, so this is called Gartner's hype cycle, and we can create such a hype cycle for any product which we build. So, for example, physics-informed machine learning, artificial general intelligence, these are all R&D topics. Whereas natural language processing, computer vision, these are already being used in the industry. Whereas autonomous vehicles, self-driving car, metro train in Hyderabad will not have a driver. It will be run by a model and it will run automatically. So like doors will open, close automatically. Metro will come and stop at a particular station automatically. Then at different turns, it will go left, right, etc. Accelerate, decelerate, etc. automatically. And there is no driver. Are we seeing that in the metro? We are not seeing that. So it is not deployed in the real world. It is kind of crossed the R&D stage. So somebody like Tesla or somebody is trying to say that they will integrate autonomous driving, but they have not actually done it, and we are not able to see it in the cars and trains, etc., which we are using. But Google search engine, everybody is using it. So it is a mature technology. So like this, there are many AI models, products, algorithms, techniques, which we can create. And we have to get to the maturity level. So whichever is the maturity level, that will be augmenting the open source software. So that would be the next step. So first you get the solution using Python, and then go beyond Python, use Scala, use different project life cycles, and then create a solution that is going to work. Okay, now how to do that? That is our challenge. So we started with a totally random list of keywords, and from that we have organized it into some open source software and maybe some proprietary software. or some hardware or even network or different technology, which will be able to give us a solution for this problem of using machine learning in our project. Now suppose your project is this. Your project is to learn how to add two numbers. Okay. How will we add two numbers normally? What is 189 plus 11? We will check that, okay, from the decimal point, find the least. Voice is audible? Can somebody confirm my voice?
Yes, sir. Voice is audible, sir, but we have muted all the participants. So,
Okay, because comments are saying voice is not audible.
yes, sir. It is clear. Some having that network issue, so might be voice is not audible.
Yeah. Please moderate the meeting. You can stop me at any time if anybody has any question.
We have given them the option. If any question, then they will raise their hands, and we will allow them to ask the questions.
Yeah. Okay. So we have to add two numbers. This is our project, and from the decimal point, go to the left. That is from the least significant digit to the most significant digit. Then in the least significant digit, find the top digit and bottom digit, 9 and 1. Then add them. If there is a carryover, go to the next digit and keep repeating this until carryover is resolved. And we know how to add single digits. So we know how to add multiple digit numbers. Okay, this is the algorithm which we, for example, in school we have studied this. Okay, so this is well known. Now suppose same algorithm has to be put to 2 plus 10 factorial. What is the difficulty? First we have to exactly find 10 factorial. But suppose I make the claim that 2 plus 10 factorial is 198. Then is it true or false? Immediately you will say it is false. And for that we don't have to actually calculate 10 factorial. We can just make an estimate. 10 into 9 is 90. 90 into 8 is 720. So already it is 720. Now again into 7, into 6, into 5, all those multiplications are there. And then you have to add 2 to it. And it will definitely exceed 198. We know that answer, right? So 2 plus 10 factorial, we don't know exactly what it is. What is 10 factorial exactly? But we know it is something more than 720. So it will be more than 198. So this equation will be false. Whereas the previous equation will be true. That is based on our addition algorithm we are able to tell. Okay. Now, what is the concept which we are understanding here? How to add two numbers? There could be any in decimal notation, any number. It could be integer, positive, negative. It can be real number, and to any number of digits after the decimal point, we can add it. And this algorithm we are using for the first step will work. This is the concept. There is additional concept of approximation, that the second step algorithm will not work. If the first step algorithm is working, that is, it is true, then the second step algorithm will not work. By how much will it not work? That can be calculated exactly. But we will make a estimate and then say it will not work. So a rough estimate is enough to verify the second equation. That is also a concept. Okay. Now the question is, how will machine learning do this? Or AI, suppose this is natural intelligence NI. From natural intelligence you want to get artificial intelligence AI. So how do you build a machine which is able to do this? And why should you build such a machine first of all? So if you build such a machine, you will get your LLM, which is giving you your relevant search results, right? So that is the advantage. Okay, so we know that what is the advantage? Why should we build the machine? We know how to build the machine. So for that, we have to understand that the machine is a program, and program takes data, and data has, in this case, what is the data? That is the first question we have to answer, which is numbers. Numbers are the data. Then what is the concept? Addition is the concept. So how do we teach this program how to add two numbers? That is the concept the machine learning algorithm has to learn. And this teaching we will do by data. So first we require data. Then we have to tell what is the right way to add and what is the wrong way to add. That we will tell by creating some equations. These equations will be represented as attribute A1, attribute A2, class or predicted attribute P. So A1, A2, P. A1 plus A2 is equal to P or not. That is to be checked. A1 plus A2 will be learned by using the digit level addition algorithm. And then wherever it does not match, we will say the equation is false. Okay. So 2 plus 10 cannot be 198. So we will write 2 plus 10 is not equal to 198. So we will give the examples to the machine learning algorithm, which are both true and false. What is the right way to do it? What is the wrong way to do it? Not do it. What is the right way to do it? And what is the wrong way to not do it? So both right and wrong combination is the concept. Okay. So this is the model. So first step is data. Numbers are the data. Second step is concept. Addition is the concept. To do the addition, right, wrong, etc. equations, we are preparing the data. That is the third step. Combination of all these data examples will be creating the model. This is the fourth step. Okay. Now compare artificial intelligence with natural intelligence. Is this how we are doing it? When we are thinking about addition, is this how we are thinking? Or is the model's thinking different from our thinking? Model has no thinking, it is only a program. Only thing is it is learning patterns like how to add. And we already know that we have memorized it and we are very familiar with the addition algorithm. Maybe 1000 years ago we were not so familiar, but now we are very familiar. And just based on the numbers, we can do the calculation and tell whether the equation is true or false. And we can tell the output of the addition. Is the model doing the same thing? This is the question you have to ask to build a better solution, the best solution possible within the given resources which we have. So this is the how of the problem. And then after the model is built, so model is ready, LLM is ready. Now give it one more example as test example. What is 99 plus 101? So if you know mathematics, you know the answer to 189 plus 11, then immediately you know the answer to 99 plus 101 also. Because it has two different ways to express 200. So if you start with 200, make it as 200 equal to 1 plus 199, 2 plus 198, 3 plus 197, so on, 11 plus 189, 99 plus 101, so on, then 199 plus 1. So 200 can be expressed in all these ways. This is coming from mathematics. So immediately you know the answer here. But does the model know the answer? Model has two limitations. To find 2 plus 10 factorial is 198 or not, it cannot stop with 10 into 9 into 8. It must calculate into 7 into 6 into 5 into 4 into 3 so on into 1. It must calculate 10 factorial fully. And the total number of operations which it has to do this calculation is mandatory for it. For us it is not, because we are happy with approximation. But because it is a machine, it has to calculate 10 factorial exactly. That is one limitation for it. The other limitation is it does not know mathematics. From mathematics, we know that 189 plus 11 is same as 99 plus 101. But it does not know that. For it, 189 plus 11 is one example. 99 plus 101 is another totally different independent example. So it has to reapply the addition algorithm, that is the model which it has learned, to make this evaluation of whether it is 200 or not. Whereas we don't do it. This is the difference between our thinking, natural intelligence, and machine thinking, artificial intelligence. Okay? And these are the limitations of the model. So, subject to these limitations, how to build our project? So we want that final product, that solution which we can take to the market and build our own startup. Okay. So how to build that solution based on the model and how to improve, what are the directions to improve the model. This is our thought process to leverage technology. So for example, if there is a bank leveraging this technology and the bank requires to give a loan to a customer, goes to the, let's say, manager of the bank and then asks for loan approval, and then manager has a software which is telling based on the historical data of other customers which are there in the bank, whether this customer fits with the credit score rating or not. And the score itself is calculated as a function in the software by taking the historical data in the bank as records in like a database where you have like different combinations of input and output, where the output is okay, give loan or do not give loan. That is the output class label. And then input is different information about the customer. And compared to the historical information, what is the current customer information who is seeking a loan and whether it can be approved or not based on the trend. So bank wants to retrieve the money. It won't give any money for free. So bank wants to give money at an interest rate to the customer and then think what is its profit in doing that. If the customer is an individual retail customer, then in retail banking, the loan approval criteria are based on the historical data. Whereas if the customer is an institutional customer, for example, Vijay Mallya's company borrowed from State Bank of India, okay, and then who is at a loss now? It is not Vijay Mallya, it is State Bank of India. Whereas you or I have gone and we want to buy one laptop and we have taken a loan from the bank. Who is at a risk now? We are at the risk. So if the transaction doesn't go through and suppose we don't get the loan approved, then we cannot buy laptop. So that is one risk. Suppose the loan gets approved and then we have to pay the interest, and suppose we don't pay, then the bank will send somebody and extract the money from us, right? So the bank is not at a loss, we will be at a loss. So the risk and responsibility is on us when we take a loan from a bank. But when Vijay Mallya's company takes a loan from the bank, the responsibility is on the bank and it is not on Mallya's company. So this is a question of how to analyze the historical data to give the credit score. And this depends on what data we are talking about. Whether it is Mallya company data, institutional borrowing, subject to all approvals of government. So at that time, whatever government was there, government of India had approved all those loans. Now those loans have not been recovered. Only the assets have been frozen. So in a different way, they have been recovered. But at that time, government approval was there. And that information, suppose we have, then the scoring model will change from what we normally expect for an individual. Okay. So all these patterns have to be found by an algorithm, which is the machine learning algorithm. And it does this by going through several mathematical models. Is it a linear model? Is it a non-linear model? Is it a probabilistic model? What kind of reasoning can we do around this? So this is all we're calling hypothesis set. So the algorithm goes through several formulae, several mathematical models, and finds the best solution, which is going to relate the input distribution X to the output distribution Y. That was being called the function F. But in machine learning, we will always get an approximate solution, not the exact value. So if you know E equal to MC square, then no need of machine learning. If you have M, calculate E. Okay? Because from laws of physics, it is coming. If we don't have E equal to MC square, maybe E is greater than MC square, E is less than MC square, E is equal to MC square depending on velocity. So E equal to MC square by root of 1 minus V squared by C squared depending on V. So suppose all this you are doing an investigation. Then what is the relation between M and D will be modeled as data set. M and all the factors affecting M will become X, and then E will become Y. Then we have to know the constant C, speed of light we should know. Only when we know that we will have the answer. That constant C will be inferred by this algorithm. But it will not be exactly 3 into 10 power 8 meters per second. It is actually some 299,158 like that it goes. So it is not exactly 3 into 10 power 8. It is something approximately 3 into 10 power 8. So that approximation will be learned by the algorithm. And the bank manager will use this software and decide whether to give loan or not. Okay. So in this you can see the various steps of building the solution. One is we should have F, other is we should have data set XY, then we should have a hypothesis set H, then we should have algorithm A. Then from the hypothesis set, the algorithm A should match with the X with the Y to approximate F in terms of G. Then this G has to be there in a software. Software has to consider different patterns like institutional and individual customers, and then from that give the score of whether there is a risk in the transaction or not. And that has to be discretized so that bank manager can understand as a yes or no answer. Give loan or not, yes or no. Don't say give loan 60% and not give loan 40%. That may be a probability which the model is calculating, but then that has to be discretized further into a yes no answer. Otherwise the end user will not understand, right? So these are all the building blocks in our project. You may compare it with any normal software engineering project and see what are the differences. So here there is an example shown of detecting image classification, detecting cats apart from dogs. So suppose we take a photo of a cat and then we take another photo of a dog. Now we want to predict whether it's a cat or dog based on the model. What will the model look like is the project workflow given here. So first of all, we have to decide how to detect a cat based on the features of the face of a cat. Those features are related to the geometry of the face. For example, we can say that the tongue of a dog will be longer than the tongue of a cat, which will be shorter than the tongue of a dog. Okay. So if you just take tongue length, then probably dog distinguishing factor is available for us. Similarly, if you take ear length, you will not have long ear cat, but you can have long ear dog. Okay. But if you just say cat is something which has two eyes, one nose, one mouth, so on, then dog also has all those things. Then you cannot distinguish. So you should find something in the cat and dog image which is a distinguishing factor. And that has to be expressed in terms of, let's say, the facial characteristics of a cat. So those characteristics will become a computer vision problem. So how to identify the eyes, nose, mouth, etc. of a cat. Then suppose we have identified the ears of a cat, and then we want to compare the ears of a cat with ears of a dog in terms of the length of the ear. And if the length is more, then we will expect it to be a dog. Okay. So this model will become the logistic regression model. It will take various inputs about the facial characteristics, and then it will predict an output saying whether it is a cat or dog based on certain information which we are getting from the geometry of the image of the face of the cat or dog. And to get the face and its components like eyes, nose, etc., we have to remove the background, and only foreground related to the face has to be isolated in the image. And in that, only those parts which are relevant for the cat dog classification like ear length have to be isolated. This is the preparation part of the data. So the raw camera image cannot be used as it is to make a decision. It has to go through these steps. And these steps are like computer vision steps, data mining steps, pre-processing steps, which are preparing the data such that it can be input to the machine learning model. The output of the machine learning model is to help us make the decision whether it's a cat or dog. Okay. So output matching to input is being done with respect to some modeling detail, like use of logistic regression model, linear regression model, and this logistic regression is a classification model. Okay, so again we go back to our library taxonomy and see that okay, we have all these steps, and then finally we are at the model, and the model is giving us the result. Now here there is no E equal to MC square. What is the relation between cat and dog? Can be told in many ways. You may define it different from how I define it. Okay, so in a data-driven way, we are giving the solution, and that is why model is the equivalent to the equation. There is no equation, but equivalent to equation is the model, and model is giving the answer based on the data input. Okay, now we have to formalize this idea. That is, we define machine learning as a study of algorithms for problem solving, pattern recognition, AI, etc. that improve upon the performance P. That is, it has to accurately tell whether it is cat or dog. Otherwise, why will you use this software? At some task T classification model, it has to build with experience E, which is data. Based on data, it has to solve for the task T. So this data can be expressed in different ways. We saw example of camera image. It can be expressed as a graph. It can be expressed as some other data structure or text or combination of different modalities of data like multimedia. All of this is valid as data. And once we have data, we will get the output performance. Highly accurate classifier, logistic regression model, 85% accurate in doing classification of cat apart from dog. Okay, so like this, we should have all these building blocks and all these steps. Okay. Now with this background, try to solve this problem. So here there is a square block on the top, then another block is there on the bottom. If it is this pattern in black and white, then it is -1, output is -1. If it is this pattern, output is +1. So now my question is, you have built your own model, okay? After checking all this framework, you have built your model. What is the output of this? That is the question. So it's a test case. This is how we will test machine learning software. Okay. So what do you think is the output? Suppose you say, you just think about it. Suppose you say all black squares are connected here. Here also they are connected. So I start with any black square, I can end at it again, back at it by traversing a path from all the other remaining black squares. Okay. So like this, I can traverse a path and come back. Here also I can do that. So the answer is +1. This is the reasoning. Okay. Now there is a counter argument which says, suppose there is a black here, black here, black here, it is -1. There is a black here, so it is -1. So depending on our perspective, how we are interpreting the pattern, we are giving the answer of both +1 and -1. This is our thinking. Okay. But what is the answer actually? Is it +1 or -1? It can't be both at the same time. Right? Both at same time is possible only in quantum computing. But otherwise it is not possible. So this ambiguity is there in our reasoning. So with the given information in this puzzle, we are not able to resolve this ambiguity. But what LLM or machine learning model will do is, it will find some pattern, like the black square. First square is black square. And then based on that, it will give the answer. So if you want it to find some other pattern, you have to fine tune it. First of all, we have to recognize there is ambiguity, then try to resolve it by giving it additional information or additional constraints or rules or guiding it in some direction. Only then it will give the answer. Otherwise, it will simply give the answer as -1. Okay, it is up to you to validate the result. This is again the difference between human intelligence and artificial intelligence. Now suppose I show you this example. This is also image classification. And then these are some images of different categories. Now, how are you distinguishing between, suppose you have to distinguish between plane and bike. How are you distinguishing between them? So for example, you will say plane is flying, bike is not flying. Bike will never fly. So fly, not fly condition. How do you know plane is flying? You look at the background and see it is sky. So this plane is in the sky. It is not parked in the runway. Whereas bike is parked. Clearly stand is there. So bike is parked on the road. Plane is not parked. It is running. It is flying. So fly, not fly condition can be used to distinguish between these two. Okay. Now suppose you have done that. Now, can that same fly not fly be applied to cat and bike? Cat is also stationary on top of a branch. Bike is also stationary on top of the road. Both are not flying. So fly not fly cannot work here. So for example, you will say cat is living organism and then bike is a machine. So machine or not machine is the example here. Living or not living thing. This is the example here. Okay, then suppose we take this example, we try to generalize it to pizza and cat. Now cat is living, is pizza living? Pizza is not living, but pizza is used for eating and then it helps you uh, address your hunger and it is consumed by living things. Pizza is a food for living things. Okay, so pizza is food. What about cat? Cat is a living thing and living, non-living will apply here. Flying, not flying will apply here. But what is the most relevant attribute? Edible or not edible is the most relevant attribute. So you will say pizza is edible. So it is different from a cat. Now you have to combine all this. Fly, not fly, and then machine, not machine, edible, not edible. All these things you have to combine to get the result for across these 4 images. Okay, so this is the reasoning which we will do in like unconsciously in 1 second we will do all this. Okay, but algorithm will require several examples and then it has to be trained to do this. The pattern which we are finding in terms of the attributes of the data has to be given to the algorithm and that pattern has to be kind of distinguishing enough. It should be able to discriminate between the different class labels. So if we take the previous attributes, fly, not fly does not apply here for this set of images, right? They are all about only living things. And you cannot apply fly, not fly here. Similarly, you cannot apply edible, not edible here. So now suppose you say this is a cat. How is this different from this? This is also a cat, right? But it is the same cat family, but this is a leopard. How do you know it's a leopard? Based on the spots on the skin of the leopard. And but spots can also be there on the skin of a cat. Then what is the difference? Maybe cat is small. If you take total length of a cat, it is smaller than that of a leopard. But how do you know the length of this leopard? This is a painting. So how do you know the length in the painting? That may be the same length as the real cat in the real world. So length cannot be used. Then what else will you use? You can say, for example, anything in real world is a cat, anything in painting is a leopard. Okay, but that is not enough. So for example, is this a painting? So you can see it is not a painting. So how do you know it is not a painting? For example, you can check in the background, there is one more wolf. Okay, so the ambiguity of the problem keeps on increasing. And what is the best way to distinguish this cat from this cat? Similarly, this dog from this dog. Then distinguish the cat from the dog using that attribute. So you have to think, for example, this dog is in the house because there is a sofa in the background. Whereas this wolf is in the wild because there is another wolf in the wild. And probably there is snow in the wild. So probably it's a wolf which is living in a snow condition. Whereas this leopard is in a forest condition and this cat is also in a forest condition. So you have to keep searching for all these attributes and finally resolve the ambiguity. Further, this has to be put into an algorithm which the machine learning will process. And without the algorithm, like how we are doing calculation in the mind, the machine cannot do that, right? So what is that algorithm going to look like? Probably there will be several algorithms. There will be a training algorithm, there will be a learning or training algorithm, inference or testing algorithm. And these algorithms will take the data. Then there is a model like a neural network on which the algorithm trains. Then it is evaluated on the data, and then it makes predictions on cat or dog. And now this has to correspond, this algorithm has to correspond to the pattern recognition scenario where we have to get the result without ambiguity. Exact answer should come, otherwise it is not functional, right? So how many such algorithms, agents, etc. should we create? That is the question for our project. And in that there are many project development frameworks available. For example, DevOps framework is there, which comes from software engineering. In that you can add ML algorithm, training, evaluation, optimization, all these steps you can add additionally. And then DevOps becomes MLOps. And then to create the ML algorithm, you require data. Solution is always data driven. So it becomes data ops. So data ops, ML ops, DevOps. This is the project lifecycle. Similarly, there is a data mining lifecycle where first of all understand the problem statement, express the use case, create the data, prepare the data, create the statistical data sample, do the modeling, evaluate the modeling on test data, deploy it in the underlying system, take user feedback, improve the use case. This is the project lifecycle. Or lifecycle can be create the training algorithm to build the neural network and then test it on a separate data set using cross-validation criteria and report the performance. Okay, so this is a machine learning workflow. Or it can be first to create the features of the problem, do the engineering of the solution in the features. That is going to set the context of the problem. Then create a mathematical model which will automatically map the input to the output features. And this model will be optimized based on several statistical criteria. It will use various algorithms like classification algorithms. And then it will have several performance metrics like accuracy or F1 score. The result of it will be used to create experiments which are to be validated on the decision which is obtained from the mathematical model. And this decision will create a feedback loop on again how to collect the data to set the problem context. This is the pattern recognition lifecycle. So like this, we can create several project life cycles, and hence we will be able to solve for the supervised, unsupervised, reinforcement, etc. learning scenarios. Now in that, deep learning will be like a tensor-based optimization technique, which we are applying for different shapes of the tensors, which are shown in the figure here, for example. So we can visualize till rank 3 tensor, 3-dimensional plot we can visualize. But 4D, 5D, ND is also there in mathematics. So in 4D tensor, for example, the cube will be there in a straight line. So if rank 1 tensor is a straight line and rank 3 tensor is a cube, combination of both is a rank 4 tensor. Similarly, rank 5, 6, etc. tensors can be defined. Their visualizations will be similar on similar geometric terms. All these tensors will be used to represent the data, such as in various application scenarios like marketing scenario, robot navigation, advertising scenario, fraud detection, cyber security scenario. In all these scenarios, we will get data, which we will represent in terms of tensors. And tensors will be used in machine learning problem to build the optimized solution. This is deep learning. This is the use of deep learning in real world. Machine learning itself can be created in terms of various mathematical models. So in terms of computer science, how to build efficient algorithms. In electrical engineering, how to create the feedback loop. In economics, what is the Pareto optimal condition in a market? These are the questions. In statistics, what are the assumptions to create like inferential statistics? And with what kind of reliability, robustness can we do this? These are the questions which we will ask in mathematics to create the deep learning solution. And the solution itself will look like this. So design a neural network, select an algorithm which will train the layers and parameters of the neural network, create an objective function for it to optimize those parameters, select an optimization algorithm like gradient descent. These are the steps which we will follow. And these steps will correspond to various classification, regression, clustering, etc. tasks. And in the task, we ask probabilistic questions like which y is most compatible with x? Is y1 or y2 more compatible with x? Is this value of y compatible with x? What is conditional distribution probability of y given x? These are all mathematical questions which will be mapped to any application domain like robot navigation, face detection, etc., decision making in stock market, etc. And the use case has to be solved for by the technology using the algorithm and model which we are building. And these are all the various models which are available: convolutional neural network, recurrent neural network, generative adversarial network, autoencoder, restricted Boltzmann machine, so on. These are the pros and cons of all these models are given here. And they will be able to process different kinds of data like text data, image data, graph data, sequence data, time series data, so on. And combination of all this will give you your what is called the representation, the sample, data sample on which the algorithm is building the solution. Okay. And then for each of these representations, there are different feature engineering pipelines which we can generate. According to these pipelines, the architecture of the neural network will change. So the simplest building block of neural network will be this perceptron model, where it is like a switch, like a fan switch. It's either on or off condition. That is the output y based on some combination of inputs x1 to xn. And there will be a weight term associated with each of these xi, x1 into w1, x2 into w2, x3 into w3. Then do the summation. So in linear algebra terms, this becomes a wx plus b kind of equation. So z equal to wx plus b. Your f of x, the f which we were trying to approximate till now, that will be expressed in terms of wx plus b. So f of x is wx plus b, and y equal to f of x is expressed in terms of wx plus b, which is a surrogate variable z is taken here. So y equal to f of x is expressed in terms of z. Z is equal to wx plus b. And the combination of w and x in this way is called a perceptron. And if this is one unit, one on-off switch which we have, several such switches can be put in series and parallel, like in the red shown here, to create the deep neural network. So this is a feed-forward deep neural network. Okay, and the output which is coming will be based on this W. This W has to be estimated based on an optimization algorithm like gradient descent. And that gradient descent has to work with W, X, B, which are all tensors. Okay. So it is called deep learning because it is having many layers and many parameters. All these can be implemented in deep learning frameworks like PyTorch, Piano, Caffe, so on, Keras, and the features of these softwares are given here. The source code looks something like this, where you create, it's an object-oriented programming. You create an object for a class, which is the logistic regression model telling cat apart from dog. Then to train that that model, you require an objective function, which is called loss function, called BCE loss, which is useful for logistic regression or classification. Then you have to instantiate an optimizer, which is stochastic gradient descent optimizer. It has some hyperparameters like learning rate. Then we create small batches of data called mini batches. And for each mini batch, for each set of mini batches, we have an iteration called the epoch. In each epoch, we have to set the model in a training mode and then give the input tensor, get the output tensor, pass it through the objective function, then do back propagation. This is the algorithm. So what is back propagation? You may please refer to literature. And then once we back propagate, we'll get those weights, Wx plus B, Ws. And then you keep doing this for every mini batch. And this is an optimization loop. As you go through this loop, you will get the solution for the parameters in the model. Okay. So when you write source code, these are the building blocks. You have to tell what is the optimizer, what is the loss function, what is the optimization algorithm, then what is the data being used, what are the hyperparameters like learning rate and number of epochs, then which model is being created like logistic regression. All this can be done in these platforms like TensorFlow, PyTorch, so on. Okay. Fine. No questions still here, right? Okay. So once we build the model, we have to put it into a mathematical framework. So one framework is shown here for empirical validation. We can build that model which is just the right fit, neither overfitting nor underfitting. It is neither too simple nor too complex. Okay, and just the right fit for the given data. And then we can test this model on separate data samples, test data, validation data, and fine tune the model based on these samples. And further, this fine tuning can be based on mathematical frameworks like computational complexity, total number of wrong predictions the model is making. And in those frameworks, we ask questions like how to put a upper bound on the total number of wrong predictions the model is giving. And how many times should we keep training the model until it is able to learn the target concept, like addition of two numbers. So these kind of questions we will ask in the machine learning.
Hello, sir.
Yeah.
Sorry to interrupt you, sir. We have a question from Nandini ma'am and Dr. Pavindra. They want once again you to explain on perceptron and also about the bias.
Okay, but we will not have time if I keep repeating the same topic. So here perceptron is taking various x's as input and it has to give the y. We want to learn the function f which will do the mapping between x and y. This function f perceptron architecture expresses in terms of a wx plus b form, where for each x there is a w multiplied like a weight, and then there is a summation which is created for each x. So in vector algebra terms, this will become wx. So basically it is a kind of a linear mapping. This wx is a linear type function, and y equal to f of z is the mapping between y and x, where z is wx plus b. The architecture for that will look like this, where each unit will be like a switch, and then you have to take all these inputs, and then these are paths which are shown from each input. It is going to every other hidden layer. So this yellow is being connected to every yellow is connected to every red, right? So this is called fully connected layer. And then the weights which are there, these W's will be on top of these edges. And then this red which is there is like a switch. It will give either +1 or -1 as the output based on what is the value of Wx. X is anyway fixed. It is input data given to us. W value keeps changing, which are like weights put on the connections of the graph. And this change will be tracked by an optimization algorithm. Typically gradient descent is used. We want to track this change such that this function f is correctly mapping y with z, as we have seen in the frameworks earlier. So x is given, y is also given. We only have to learn f here. Now in a normal C program, what will you do? You just take x, then keep on calculating and you'll get y. There is no f. Here the goal is to learn f. This is how machine learning will be different from a normal program. And that f will be expressed in terms of these w's which are there on these edges of the graph. And the way we adjust those w's such that predicted value of y matches the actual value and error is minimized in the neural network. That is the backpropagation algorithm. And this is only one unit, one layer we have seen, one fully connected layer. Like this, if we have some other convolutional layer, recurrent layer, different architectures will come. This is the architecture called feed forward architecture. From left to right, we have to read it. Whereas in other architectures, then I will show some diagrams. There will be other ways to read it. And that topology which we are getting, that has to be optimized for these Ws. And which algorithm will do this is something we have to design. Okay, and then this one here, basically we want to create the correct fit of the data model to the data. It's a statistically good fit, and it has to be encoding information from the data, like data distribution, sample, etc. information, statistics information, such that it is doing the classification, regression, etc. task. At the same time, it should not be very complex model. At the same time, it should not be very simple model. So that will be available in the white space here. For example, this objective function, suppose I assume that if we optimize for this objective, we are also minimizing the statistical error. That is, the accuracy of the performance of the model is going up if the error is decreasing. So this will always be a decreasing curve. And then here, if the model is too simple, then it won't work on all test examples. So that is called underfitting condition. If the model is too complex, then it will work only on training data. It will just overfit to the training data. And for other data, it will not work so well. We don't want either underfitting or overfitting. So we want this white region. Wherever the errors start increasing, we want to stop training. So total number of iterations for which we will train the algorithm, like 50, 100,000, will be decided based on this. Similarly, we can have other parameters which are affecting the training of the model also on the x-axis. Our goal is always to minimize the value on the y-axis to reduce the error. Same thing can be put into mathematical model also. Like what kind of upper bound can we give for the total number of errors which the model makes in predicting a particular class label like cat or dog. And what is the computational complexity of this problem? How much data is required to solve for this problem? So all these questions we can ask. So basically we don't want too complex nor too simple model. Okay, and it has to be a model which fits to the data. So this is the calculation which is done in a normal neural network where you will get the output. Output will be expressed in a layered fashion in terms of the input. And then we have to find the derivative of the output with respect to input. That will also be expressed in a layered fashion. And numerically, we are able to approximate the value of the derivative. From that, we are able to tell whether to adjust the weight by increasing or decreasing it on every edge connecting the activation units in the layers. That is the red and the edges with the red lines which are there. There will be a weight associated with every line. How to adjust this weight, increase or decrease it? That we can tell based on the back propagation of these gradient value, derivative values. Based on the chain rule of calculus, these derivative values will be updated into these weights. And then different data distributions. So some of the common ones like Gaussian distribution, log normal, gamma, exponential, geometric, Bernoulli, uniform. All these distributions are shown here. Based on different distributions of mapping the input to the output, that is the pixels and geometries of the cat versus dog problem to the labels of cat and dog, that will be expressed, different distributions and changes on them will be expressed in terms of these weights. And this final weight will converge to some solution. And finally, we are able to make a prediction. Is it a cat or dog? Also associate a probability with the prediction. With how much confidence are we telling that? And the probability distribution for various cats and dogs can be plotted, and the residuals and mean and view and variance and moments etc. of the properties of the probability distribution of the predictions can also be analyzed. Okay, now I will just switch to I'll see if there is any architecture available for LLM. And then I'll switch to quantum deep learning. Yeah, something like this is an architecture. This is one example where we have the feed-forward neural network, but we also have convolutional neural network. It is encoding the image data using the convolution operator. Then it is regularizing the information using the pooling layer. Then combination of this and the feed-forward network is giving us the answer in the medical case, where we have different inputs like EEG data, ECG data, X-ray data, so on. And these are all the neural networks which are commonly used. Convolution neural network is represented like this normally. So each convolution is like a cross correlation operation, and it is done in one batch of pixels against another batch. So you have like a filter, like a small image, filtering image on top of the image, and you keep moving it. And then different steps which it takes, you find cross correlation between those steps. So you compress the image. Then you keep on reducing the dimensionality of the image, like 32 by 32 by 3 image, you will make into 2 by 2 by 10 image. And then you will add this pooling layer, which is like a kind of a anchoring weight on top of the weights which we are estimating, so that they don't become too large or too small. And then fully connected layers are there, like in multi-layer perceptron. And final output comes whether it's cat or dog. Similarly, if we do it instead of image, we put a graph, then it becomes a graph convolution neural network. And if we change the architecture from left to right architecture to this kind of architecture, so input is coming from down, and then input here is going from right to left. Okay, then it is also going from left to right. Okay, like how you will write like Hindi in left to right and Arabic right to left. Okay, so that is the data flow. And then the dependencies between the different activation units here it is bypassing. So here it is input like this, then output is coming like this, then it is also coming like this. So it is by this from here the input is bypassing this unit. Similarly, that bypassing connection is there in every vertical slice. Then combination of all these different paths which are possible gives you this sequential model. That sequence model is able to learn things like relation between words. So in your LLM, how is one word related to the next word? And what is the meaning of the sentence? This information is coming from the sequence of words. And for each combination of these sequences, we have to get these bypassing connections. Okay. And then this is happening with respect to different time points, like basically first word, second word, third word, fourth word, the relation between first word and 10th word, relation between third sentence and fifth sentence. So all this is being encoded here. Now, if you combine this with convolution and also use fully connected layers, then you get a hybrid architecture. And also the building block, this activation unit here is called a LSTM. In again LSTM, there are 4 activation units. So we saw only switch kind of activation unit. So instead of that, if you use a tanh function, or if you use a sigmoid function is 1 by 1 plus e power minus x. Okay, tanh is e power x plus 1 by e power minus x plus 1. Okay, so you use these functions here in this way, then put the connections like this. There is a feedback coming from the previous prediction. It is going to the next prediction. And then there is a input also coming. So there is an encoded in signal which is coming in H, and there's an input coming in X. Combination of both of them you put through these gates, and some of these gates will switch on and off, and you'll get the output. And also feedback for the next unit. So this is one unit, which is this unit here. It is called long short-term memory unit. So this is one architecture. Like this, we require like a block diagram around this. So let me see if there is any block diagram here. Yeah, something like this is a block diagram where combination of different steps is involved. Classification is also happening, association is also happening, encoding, decoding is happening, inference is happening. All of these combination is one block diagram. And then yeah, it is not there here, but we see in the other set of slides. If there is any block diagram which uses LLM. Yeah, so here's one example. Let me share the screen. So here there is a graph coming from some biological information. Then it is being encoded. The encoding is also done with a tokenizer, that is sequence data. So this is like graph data. This is like sequence data, like DNA, RNA sequence data. Sequence data will be expressed in terms of tokens, that is features. There will be like a numeric vector associated with mapping of each sequence to the neural network. And this numeric vector plus this graph encoded information is being fused, combined. And this combination is going into text data. Text is another like doctor prescription. So text data is being combined here with a fused model output, and attention mechanism is applied there, which is like a sampling technique. And in between that, the GPT model is used, which is LLM. So the LLM's output will be like a encoded information. And this encoded feature vector, like a vector of numbers, can be combined with other modalities of data like graph and sequence. Then again, one more language modeling head is there, which is creating an objective function for doing all this combination, such that output will be giving some information related to protein function. Okay, so this is one example of how the block diagram combines the different components together. So these are the models, the components models: transformer, generative model, variational model, energy based model, diffusion model, so on. And each of them is built for different type of data like graph, sequence, etc. Yeah, this is an example of a question answering system, how LLM creates the answer. So question is coming from here. Then question is a pattern recognition problem. Then the scope and context, etc. of the question is broken into different answers. This answer generation will be based on an information retrieval workflow. All of these steps will be there in the backend. And the backend architecture will look something like this, where you have database from which data is coming. And you have to map it to the query and different components like keywords in the query. Then you have to get the results which are relevant, like semantic information in terms of paragraphs, sentences, etc. And then it has to be ranked, and recommendation kind of solution has to be given to the end user. This is another simpler workflow where you have question, and from question, how do you come up with answer? is based on first you process the question, then you find the document with the answer, then you summarize the answer. So the summarization will be output of a graph like this, neural network. Okay. So this is a sequential neural network because these bypass connections, all these different left to right to left, all this is there. Okay. Then this is called encoder. Mirror of this, if you put a mirror here, that creates a decoder. And encoder decoder's output is being combined like with some sampling mechanism. So there are different ways to do this. For example, these are all the RL algorithms to do this. Okay. And these are the different layers on how words in a sentence are represented. So suppose you want to create a score on a sentence, like a sentiment score. Then the RNN will take inputs like this, and then outputs will be like some description, meaning of the sentence. Then dependencies between the different words in the sentence are shown here with these units. Different paths are possible, like here straight path is there, here this path is there, here this path is there. So many to one, one to many, these kinds of many mappings are possible. And we already saw this LSTM cell. This is normal activation unit. This is another cell. This is RNN cell. Only tan H is there. Here tan H is there, sigmoid is there, 3 sigmoids are there. Then forget gate is there, input is there, feedback is there. So this is more complex. This is somewhere in between. 1 tan H, 1 sigmoid is there. Okay. Then this is the architecture which we will create. This is another example. So you have to think in terms of like nested hierarchy. So units are there, then combination of units is there. That itself will create one more unit. Then that will be combined again. So that is why it is called deep learning. And then this is the mathematical formulation. So what is the memory component? What is the connection? How much information is passed? What is relation between input output? Yeah, basically this is going to lead to many parameters. And then we will analyze the data in a very fine-grained way. For example, here ECG data, ECG data is given as a time series. What the doctor looks for is the intervals between the peaks normally. But between them, the various steps which are there are the features, the information which we want from the time series. Different intervals are being used. And combination of all these intervals is going to give you more information between the two peaks, which will help the doctor make decisions. Yeah, I think we can move to quantum computing and just seeing if there is any infographic on the total number of parameters which are there in this model. So essentially these are very large models. Many parameters are there. They will require a lot of computing capacity, like a data center would be required. And the total number of parameters will be more than 1 million. So this is an example of a generative adversarial network and how it generates images. So it just starts with noise. It goes through all these convolution layers. Its goal is to create a clean image. This is a generator neural network. It competes with a discriminator neural network. Job of the generator is to generate fake synthetic data. Job of discriminator is to catch that fake data like a policeman. And then the interaction between both of them is going to lead to optimization solution. In the equilibrium solution, the raw white noise kind of image will be transformed into some meaningful image. And this image is a synthetic data. Such a person may not exist really. Like you take all LinkedIn profiles, generate these images. You can create a fake LinkedIn page like this. And the different layers which are used are shown here: convolution, upsampling, fully connected, mini batch. All these layers, color coding is shown. And the equations will be something like this for these layers. So the objective function for training the neural network is this. Basically, the discriminator is the policeman. Generator is the fake counterfeiter kind of scenario. Policeman competing with counterfeiter. And this is solving for a probability distribution of the original data. So the generator is able to reconstruct that original data and generate fake data also. Workflow will be something like this. Generator is able to create patterns out of random noise. Synthetic data is the output, random noise is input. Generator is competing with discriminator, which has to distinguish between real data and synthetic data based on a loss function, which the generator has feedback loop on. So this is based on game theory. So I don't think we'll have time for game theory. So this is example of generated data, where you have 7, then 1, then 9, then 0, then 8, then 3, so on. Okay. So it is a continuum. From 7, if you remove the top left part, you will get 1. If you add a circle, you will get 9. So from 7, you can get 9. For the neural network, it's a continuum. How it does the geometric transformations from 7 to 1 to 9. So suppose it makes any mistake in this continuum, then it will make mistake on all this entire distribution. And we have to study all these mistakes to actually use the neural network. So this is how the autoencoder creates a encoded search space for the handwritten digits 0 to 9. Various color coding is shown. So all the zeros are here, then all the 9s are here, all the 7s and 8s are here, all the 4s and 5s are here, 5, 6 is here. Okay, so on. 2 is here. So this is the geometric representation of the handwritten digits, which the neural network is creating. And the architecture of the neural network is this. This is called variational autoencoder. It takes any input like handwritten digits and it projects onto some statistical parameters like mean and variance. And it does this in a latent space, in a different search space. Then it reconstructs the input. Input is X, same input has to be output. Some X dash will come, X dash minus X should be close to 0. So these are all the various models for audio, video, image, text, sequence, graph, other modalities of data. These are only one class of models, which are the generative adversarial networks, only one class. Like this we can get for many other models also. And we can combine all of them into architecture also. Okay, thus we will get deep learning. Deep learning will act like a tool to optimize machine learning. Machine learning will be part of artificial intelligence. Artificial intelligence, we have to guide it to create the result we want. Okay, I will just quickly go through quantum computing. I don't think we have time. We have to close in 10 minutes, I suppose. So this is how quantum computer looks like. It is made from gold. And basically you have to understand the idea of qubits, which are different from normal bits which we have in computer. It gives us ability to process in parallel and also encode more information in less bits. So it is based on superposition and entanglement phenomena of particle physics, where two kind of particles are there, physical particles are there, which are interacting with each other in like electromagnetic interaction. And then the information capacity which we want will be based on the charge and the spin of these particles. And we can leverage different ways to get a range of values for these charges and spins. Spin can be clockwise or counterclockwise. Charge can be between 0 and 1. So it's like an interval of values. Whereas in normal bit, we have only two possibilities. It is either 0 or 1 state. Whereas in quantum computing, it is 0 state, 1 by 8 state, 2 by 8 state, 3 by 8 state, 6 by 8 state, 7 by 8 state, and 1 state. So 8 states will be there in quantum computing. So in binary, in Boolean logic, you have only 2 states. It is either true or false. Okay. In quantum logic, it is 8 possibilities are there. Partial truth and partial falsehood is also accepted. So uncertainty and probability will be associated with every quantity. And we will express it like a matrix like this. And we will say that any information which we want will be put into the bit using combination of complex numbers, which are having some weights on the states of the particles. And this combination will be in terms of what is happening in one particle when the other particle is in some direction, like it is rotating in this direction. It is pointing in this way. What is happening to other particle? That is called entanglement. Then combination of this particle in this way, the other particle in this way, that how does that encode information? That is called superposition. So we will express this using this Dirac notation, basically like complex numbers, and also like fuzzy logic kind of thing. So 8 bits are possible. Huh? So for example, if I say it is raining outside, how will you prove me right or wrong? You will actually go outside, and if you get wet, then it is raining outside. If you don't get wet, then it is not raining outside, right? But suppose we are in like a foggy kind of situation. So it is kind of rainy, foggy kind of situation, but it is not totally raining. So that situation can also be described in this logic. So the truth claim of any statement, even partial truth is accepted. So for example, I know how to talk in English, but that does not mean I don't know how to talk in Hindi. Okay, so Indians have 3 language formula. So they will know their mother tongue, they will have Hindi, then English also. So they know 3 languages at the same time. At least 3 languages, more than 3 also possible. So it is not that we will talk only in English. So it is not that statement only in English will be made. No. It will be made in Hindi also. You can have combination of Hindi and English also. So these kind of situations can be expressed in terms of quantum logic. And there is this Hilbert space, which is like a search space, different from normal search space which you have for machine learning. It is infinite dimensional. So it is a very, very large search space in theory. It is coming from subatomic particles. And that is used in machine learning. You can do many more computations than normally possible. In a very optimized way, you can get the answer. But there is every result is only probabilistic. It is not deterministic. So we cannot exactly say what it is. Okay. That is why there is a probability associated with every claim. And even in terms of the information content which is encoded into the bits, there is a probability associated. That probability will be expressed based on the particle wave nature of reality. So like you take any electron or photon or some such particle, it can be in both the particle state and the wave state at the same time. And this is the Heisenberg uncertainty principle. So we create a Schrodinger wave equation for this. So we have to solve for that wave equation to get the answer in the machine learning problem. So the input will also be complex numbers, output will be complex numbers, and then model will also be complex numbers. Advantage of this is you can encode more information in less bits, because 8 states are there instead of 2 states. Suppose you have to encode number 8. Okay, you require 4 bits normally in current notation, but 8 will be encoded in 1 bit only in quantum notation. So in qubit, 1 bit is enough. For normal computer laptop which we are using, 4 bits are required. So 4 bits job is being done by 1 bit. That is one advantage, because you will just say 8 possibilities are there. So the number 8 will correspond to the 8th possibility. Okay, but because only 2 possibilities are there with bits, you require 4 bits, 1 0 0 0. This is 8. And you can parallel process all these bits. Each bit is independent. Only dependency between them is this entanglement phenomena, quantum entanglement. Entanglement is like, okay, before I say something, you already know what I'm going to say. So it means that you know me very well, and what I'm thinking also you can tell. Something like that. So there is like entanglement between your thinking and my thinking, something like that. So that is there between all particles in the universe actually. So when one particle changes its state, like spin or charge or something, all other particles in the universe know about it. How do they know? It is a mystery, but we can use it for information capacity purpose and computing purpose. So you can see that so many bits, 10 power 90 bits are required. Okay, 10 power 90. So 1 followed by 90 zeros is required normally for a very large supercomputer kind of capacity. And that can be achieved in only 300 quantum bits. So already Chandrababu Naidu has taken that thing already has, I think, some 1500 quantum bits. So that thing, when that computer goes to the next version, in 5 years or so, we will get 300 bits. And it will act like a supercomputer. So this is the advantage. Now you can apply it in any area like agriculture, education, governance, anything, right? You can apply in any area. Same advantage like supercomputer it will give. Also, there are many interesting directions at the intersection of machine learning and physics, which are possible from this. There are, for example, there is an area called mathematical physics, and it is actually very interesting area. So, like how in +2 we had studied, for example, trigonometry, geometry, calculus, these kinds of subjects, and then we saw like number theory, for example. After that, we did not see number theory. When we do engineering study, we don't study number theory. But number theory has a lot of Indian contribution. For example, Kerala School of Maths is there. In Kerala, mathematicians were there who developed calculus, and number theory was used. There were ideas like infinite series which were developed there. For example, Aryabhatta is famous for finding the value of pi as an infinite series, and it is required to calculate like celestial constants like diameter of Earth and like motion of planets and other things. So Aryabhatta was looking at the entire solar system and calculating astronomy, astrophysics, and their value of pi was something he calculated. It was based on infinite series. This was perfected in the Kerala School of Maths before Newton, few hundred years before Newton. And calculus came from India only. So this is the basis of quantum physics. And the subject which studies this in physics is mathematical physics. In that, number theory shows up. Infinite series, number theory, all these show up in mathematical physics. Now from mathematical physics intersection with machine learning, we can come up with new neural network architectures like LLMs. next generation of technology can come. So LLMs also came that way only. The language models, etc., came from last 20 years of development. So like that, quantum physics we can drive next 20 years of development. Not only that, the machine learning algorithms, like some optimization algorithms, can be created from mathematical physics. So there are many theoretical connections between physics and machine learning, which will lead to next generation of technology. One such connection is this decoherence, quantum decoherence, which is related to basically randomization in the quantum data. So you have to take like average. For example, you have released a gas into a room. So you have released, for example, something. So we have oxygen and carbon dioxide here, but you have brought hydrogen, for example. Okay, hydrogen is there in a cylinder. You have released from that cylinder into the room. Okay, how hydrogen atoms, molecules, etc., will diffuse along with oxygen and carbon dioxide molecules into the room, and it will spread all over the room. Okay, that cannot be calculated at each molecule level of hydrogen. It has to be done in an aggregate way, like in the entire volume of the room, in which direction is the gas going. Okay, and then average result we will get at T plus 1, T plus 2, T plus K, how the gas is getting mixed up. That average value will be based on the individual atom and molecule level what is happening. For atom molecule level we can write physics equation, but for the average level we cannot write. Okay. It is a kind of optimization solution. We have to see in the optimum solution what is the mixture of the gases which is there in the room, and this has to be kind of a generalization from the equations of physics. So the equations will be like some differential equations coming from calculus, and we can solve for this optimum condition using machine learning. And new algorithms can be developed to compute how this optimization will come. And quantum computers like GPUs will give the hardware capacity to do that. Although we don't have quantum computers right now. Okay, so we have only limited number of qubits available because there is this issue of noise. So it is, how will you leverage noise? Noise is random noise. If it is random, there is no pattern. But if there is a pattern, you can use it to improve your solution. So is it that noise has pattern but we can't find it? Or is it that it is totally random and there is no pattern? So based on this, the hardware of the quantum computer, based on this solution, hardware will be getting improved. Some of what we have hardware now, that itself is very innovative. But when it becomes mature technology, then these quantum decoherence kind of ideas will be very much helpful in creating the machine learning solution. Okay. So in theory, I am also doing some research in this area, and it seems to be producing results. We have already covered all this. Let me just show you about quantum computing, some more points. So there is this quantum speed up, which is always discussed. That is how we will get more work done in less time. Computational complexity advantage will be there. And some of the algorithms which will be based on this are like classification optimization algorithms. Some of the issues in those algorithms are listed here. And some of the hardware circuits, like in VLSI circuit today, and or not gates are there. Like that XOR gate or the swap gate, HADMAT gate, these are the gates which will be there in quantum circuit. Okay, I think we can stop here. If you have any questions, you may please post.
Thank you, sir. Thank you, sir, for enlightening us on hype cycle for artificial intelligence 2021, the importance of historic data, and how word relations in LLMs are formed. Uh, yes, through CNN and deep learning. We have one question, sir, here, where T. Bhaskar sir asks about why is GPU computation important in deep learning?
Because linear algebra operations are there in deep learning. The tensors which I showed you, we have to multiply those tensors in convolution operation. We have to decompose those tensors to get dimensionality reduction. We have to represent the data in terms of those tensors, then create like objective function optimization algorithm around that. So it's all about matrices and tensors. And we have to get like a sparse representation, all mathematical properties it has to satisfy. This operation is possible only by moving blocks of numbers in the computer circuit, in the micro architecture of the processor. In normal CPU, you have the ALU unit, which is doing addition, subtraction, etc. operations, but you don't have specialized units for these matrix operations. And in GPU, that is there. The CUDA software, etc., is doing that only. Further, GPU does parallel processing. So because this is having many parameters, order of billions of parameters for each model, we require to have an efficient solution. And the way NVIDIA is the market leader, NVIDIA is doing it is with respect to parallel processing on multiple cores of the GPU. And lot of computing elements are packed into less like few square inches of area. Many computing elements are packed in. You can just see any NVIDIA like RTX kind of server specification. You'll see that it is very dense. And already we have hit Moore's law, that is more hardware innovation is not possible. Like how we have hit peak oil, more oil is not there. So only renewable energy is the only option. This parallel processing of the linear algebra operations has to happen in the processor. And the normal CPUs don't have this capacity. They don't have these hardware elements. They have their limited scope, but for especially these because of the depth of the neural network, normal neural network in Python can be built on CPU, but it won't be so accurate. To create like LLM type models, we require a whole data center of GPUs. And this data, to maintain this data center itself, we require a lot of power, electricity, then water to cool it, then manpower. Humans have to human oversight is required. Companies have to invest in this, but the return on investment is not much on this because they, for example, in somewhere near Vizag, if AP government will put a data center of Google, that data center will improve the service of Google in India. Like if you are using Gmail, etc., Google Apps in India, that will be made better. That is the business advantage. But the natural resources from the ocean water, from the power distribution, etc., which the data center is consuming, cannot be reused. Once the power is consumed, it is gone. Like that, once the water is circulated, it cannot be used for drinking purpose or anything. So there is a lot of resource crunch, and natural resources are required to maintain these data centers. Without these data centers and GPUs and advanced hardware, we cannot run these LLMs and these AI models. So this is actually a big problem. The AI models are outpacing the natural resources which we have. So eventually, we will not have enough water, enough current and all these things for the data center. The only other option is to redesign all these architectures, make them more efficient, compressed. Like earlier, if you see 50 years ago, the server which was there, if you go to a server room and see the server, like IBM server, whatever capacity it had in terms of memory, computation, storage, etc., is nowadays there in your smartphone. You take any Samsung phone or iPhone, that phone will have that capacity which the server had 50 years ago. So which means we have moved all that server capacity to the phone, and we are using phone in our house. We don't have to go to a server room for it. So similarly, something like this has to happen with the data centers, and the entire capacity has to be some kind of a leap in the capacity is required. But that is not possible because we have already reached the peak already. Moore's law, which says that every few years the hardware capacity will double, that we have already finished. So this mobile phone example won't work here. Maybe quantum computer or something will work, something like that will work. So only when quantum computer comes, the LLM will be sustainable. Otherwise, it will create a big problem. So India getting Google's data centers, 1 or 2 data centers is okay, but getting 25, 50 data centers is going to take away all the natural resources like water supply from normal human beings to data centers. So this is a kind of trade-off, and it is still evolving. But without all this, you cannot solve the linear algebra type problems. Mathematically, they were solved several decades ago. But technology is the main bottleneck here. Only last 5 years, big data, GPU, like this, many developments have happened. It's a convergence of technology which we are seeing now in all the generative AI, agentic AI, quantum AI, etc. applications. But how sustainable it is under question. So GPU, it is not only about GPU, it is about computation and how we will design the hardware around that. And India doesn't have any capacity to create its own chips. All chips are imported from Taiwan, Korea, other places. So this is going to be even bigger problem. If we are only going to import all technology from everywhere in the world, we are dependent on them. So if they raise the charges or some change the technology or something, we are dependent on. We don't have, for example, electric vehicle battery technology. Okay, we don't have Air Force plane jet engine technology. So we don't have many things. Unless we do innovation, we will get into serious problem later. Okay, next question, please.
Yes, sir. Sir, Bridget Sahani sir is asking how we will perform quantum parallelism in quantum computing.
Basically, sir, it is related to the bits and how the bits are working in entanglement and superposition. When we look at superposition principle, the complex number which we have, that partial complex number which is encoding the information like 8 in quantum bit, that partial information is independent of the other partial. What is dependent and what is independent? So long as it is independent of the other qubit, it can be processed in parallel. It is not waiting for the other operation to complete. In normal bits, like in a computer, you have a sequence flow to process the information. That is not required in quantum computer. But at the same time, there is this entanglement phenomena, which is about the interdependence. And so long as we can utilize it to advantage of encoding into the circuit, we will get the optimal solution. So long as we are able to manage entanglement, we can do parallel process. Okay, next question.
Yes, sir. Thank you. All are giving feedbacks, telling that it was really a very informative session. Participants, we request you, all of you, to switch on your cameras for a moment so that we can capture a group photo to mark this FDP session. So thank you, sir. It was really a wonderful session. I learned very good things like LLM architectures, how deep learning and CNN is helping out there, and why quantum computing. And right now with the question, I also got to know that quantum computing or LLMs is going to pull out our natural resources. Bit worried for that point. Really very insightful session, sir. Thank you so much.
Okay, thank you.
Participants, requesting all to switch on your cameras so that we can take a photo for this FDP session. Yes, thank you. Thank you all.